All right, so this is our first video of our online adventure. And in this video, what I want to do is to cover some more material from chapter 12. If you remember, we've moved into dynamics, and we're actually specifically right now, we're looking at kinematics. So we're basically getting expressions for velocity, position, and acceleration of an object as it moves. And when we do kinematics, the thing that makes it sort of special, or its defining quality, is that we're not really concentrating on why the objects move that way. We're just sort of given a starting point, like this is what the acceleration looks like, or this is what the velocity looks like, and then we go from there. In the next chapters, we're going to start to look at forces and then get the same expressions, but start with F equals ma and go from there to find these types of expressions. So just to remind you, last time we reviewed, the fact that the acceleration is the derivative of velocity with respect to time. And of course, velocity is the derivative of position with respect to time. And we talked about how the fact that you can use these expressions and integrate, if we do what we call separation of variables, and integrate both sides of the expression, you can find expressions for acceleration as a function of time. Well, that's probably what you started with. Velocity as a function of time, and position as a function of time. One of the specific examples that we looked at was for constant acceleration. And so we start off with the idea that this is a constant, just some value, and then we integrated. And from that, we come up with these expressions like S is equal to S naught plus V naught t plus 1/2 AT squared. V is equal to V naught plus AT. And, one of the things that I tried to point out in class that the other day when we went over this is these expressions, I hope, are pretty familiar to you. And for instance, if you see the expression for the position as a function of time and you notice that it's a quadratic, that should click in your head immediately that that's a constant acceleration situation. And then also you should be able to pick out, what's the initial velocity of this object, because that's going to be the coefficient of the time piece. And half the acceleration is the coefficient of the t squared. So those are some things that I hope that you're getting a little bit more comfortable with. The other thing that we did is we realized that we could rewrite the definition of acceleration using the chain rule. And what we're doing there is we're trying to do a change of variables so that instead of writing things in terms of acceleration and time and velocity, we're going to write it in terms of position and velocity. And so, for instance, A ds equals V dv. And in the case of constant acceleration, this actually gives us the expression, another expression you might remember from constant acceleration problems, is where we look at how the velocity and the acceleration and the position are related to each other. Notice that in that situation, what we've done is we've eliminated time. And so we could do that algebraically, or we can do it this way. This is going to come in handy because sometimes you might be asked in a particular situation, you might be asked to find what's the velocity when the position is this. And so if you are able to find a relationship between velocity, position, and acceleration directly and not have the time as a piece of it, you can get at the answer a lot more quickly. And so, of course, we did look at an example of that. So now I'm just going to talk about some things like in more general. So first of all, we're just going to talk about just general motion along a curve. And so, for instance, here we have a path. That's the blue line that's labeled S. And we have an object moving along the path. And its position vector, we are measuring from the origin, and so that's R. And so you can see that as that object is going to move, it's going to, that R position is going to change. So in this case, we might talk about just how R depends on T, and also realize that the magnitude and the direction of that position vector may change with time. So for instance, in this picture here, we see that, this is at one time, so this might be a time t, and then this is at time t prime. The object has undergone a displacement, and so in the time delta t, the object went from r to r prime, and so it underwent a displacement of delta r, which would be r prime minus r, because it's always final minus initial. And so this represents the delta r, represents the displacement. And then if we look at the velocity, sorry, not all of our symbols are translating. Our average velocity is just going to be that displacement over delta t. And then, of course, if we want to allow the time interval to go to 0, we have the instantaneous velocity, which is the derivative of r with respect to time. And these should be all deltas. One of the things you might remember from general physics is when you have an object moving along a curved path, or really along any path, the velocity vector is always tangent to the motion. And so if we have a curve like S that shows where the object is and at different times, we know that the velocity vector can always be drawn as a tangent to that vector. That's going to be different for acceleration. So the average acceleration is the change in the velocity over the change in time, where, for instance, you see here that as the object goes from this point to this point, its velocity vector changes. It can change in length and it can change in direction. If we put these two vectors tail to tail, like in this picture, we can say that the vector that joins their two heads is the change in velocity. And now the acceleration vector is going to be in that direction, in the same direction as delta v. But this path right here is not the path of the object. This is also actually just talking about the path of the acceleration vector, which we call the hodograph, just to represent that. The instantaneous acceleration, of course, is the derivative of velocity with respect to time, or it can be written as the second derivative of the position with respect to time. Again, I apologize that my subscripts aren't coming out in this picture. All right, we already talked all about that. Okay, so sometimes we could, if we have something moving in a curve, we can still express it in our rectangular coordinates, our x, y, and z, using our unit vector I, j, and k. And so vector r can be written as having an x, a y, and a z component. And x, y, and z can all be functions of time. And so that means that they might, be some algebraic expression that depends on time. When we do this, we can also talk about how long the position vector is. The position vector is still going to be found by basically the Pythagorean theorem, where you take the square of all the components and then you add all those squares together, and then you take the square root. The unit vector in the direction of r can be found by taking vector r over its magnitude. Oop, sorry. So for the velocity vector, the way that we would find it, because it's the derivative of r with respect to time, we would take the derivative of each of the components, and each of those components would represent the components of the velocity. So dy dt is the y component of the velocity, dz dt is the z component of the velocity. And then the magnitude of the velocity vector, again, we're going to use the Pythagorean theorem and take the square root of that. And again, reminding ourselves that this velocity vector right here is tangent to the path. The acceleration vector, of course, is the derivative of velocity with respect to time. And so we could write it as dvx dt in the i-hat direction, the derivative of vy with respect to time in the y direction, and the derivative of vz in the z direction. It could also be expressed, well, another way to write this is ax plus ay plus az. So each one of those are the individual components of the acceleration. We could also represent each of those components as the second derivative of the position, just to kind of keep in mind that it can be thought of in a lot of different ways. And then again, the magnitude of that acceleration vector, we look at all the individual components, we square them, and we add them together. And again, here notice that it's not necessarily true that the acceleration vector is tangent to the path. It doesn't have to have any particular orientation. Okay, so here is an example of where we might sort of use our information and see if we can figure this out. I'm going to do the first part, and then I'm going to ask you to try to do the second part of this question. And that's something that we'd come back to when we have our meeting all together. So some of these absence of subscripts might be confusing, so I'm just going to rewrite this. The y equation is 0.05 x squared. Vx is equal to minus 3 meters per second. Ax is minus 1.5 meters per second squared. And x is equal to 5. So these are just pieces of information that we've been given. And so from this, they want us to find what is Vy and what is Ay. So Vy, we know, is the derivative of y with respect to time. And so we're taking the derivative with respect to time of the expression that we were given, 0.05 x squared. Now, it seems at first like maybe this is incredibly simple, but we have to remind ourselves that because our expression for y is expressed in terms of x, when we take the derivative with respect to time, we're going to have to use the chain rule. So first, we'll take the derivative of this expression in the parentheses with respect to x, and that's going to give us 2 times 0.05 times x, but then we're going to have to multiply it by dx dt, because that's using the chain rule. So this is sort of like dy dx, and then multiply it by dx dt, and that gives you dy dt. Okay, and now you'll see why they gave us a lot of that information. It seemed kind of, why do I need to know that? So the 2 times 0.05 is 0.1, and then we put in a value for x where we told that x was equal to 5. dx dt is vx, and so that's minus 3. And so the value of all that added together is minus 1.5 meters per second. So the next thing is to find the acceleration in the y direction, which is equal to the derivative of vy with respect to time. Now you have an expression for that, for vy, it's right here. So you're not only going to have to use the chain rule, but you're also going to have to use the product rule. And so I want you to try that, and then that's something that we can look at as a group when we come together. All right. Okay, so now we're going to sort of move along to look at some different things. We're going to look at that curvilinear motion again, but we're going to use look at it, instead of doing x, y, and z, we're going to use 2 components, a normal and a tangential. One of the things I want you to think about when we're using different coordinates is we always use different components that are perpendicular to each other. If all of our components are mutually perpendicular, we can sort of cover all the motion by using those individual components. So in this picture, we're asked for, like, okay, well, you've seen this pattern before on a highway where you can do on-ramps and off-ramps using cloverleaf. And you know that if you drive your car around in that sort of roughly circular shape, that your car is going to be experiencing a change in speed and also a change in direction. So it has an acceleration for 2 different reasons. It has acceleration because the speed is changing, and it also has an acceleration because the direction is changing. And so we want to kind of figure out how to write those 2 components of acceleration. Think about why you would care about the total acceleration. Well, for instance, the normal acceleration, which also might be thought of as the centripetal acceleration, is going to be important because it's the acceleration towards the center of the curve, and that's the thing that's going to be responsible for keeping the car in that curvy shape, in that curvy path. And you might think about eventually, well, what forces are responsible for that, and will they be strong enough? Because if you go around those ramps too quickly, your car is not gonna go well. Your car is gonna slide. And think about, why that's true. And that's one of the motivations there. I'll let you just kind of ponder that. Okay, so here we're talking about the normal and the tangential components. So a couple things that we're thinking about is, for one, we are kind of following along with the particle so that the direction of our unit vectors is going to move and change direction as we go along the path. So for instance, the direction of the normal and the tangential are different than they would be when the particle is right here, and this would be the normal and this would be the tangential. But in any case, those are our 2 sort of components in this idea when we're using this idea. The tangent direction is always going to be in the positive direction of the motion, and then the normal component always goes towards the center of curvature. So for instance, actually when we're going around like here, the center of curvature is over here, but if we would change and continue along, the center of curvature would move over here, and then there would be the direction of the normal. So think about that. So here are our unit vectors again, and they're just showing you, this is actually a better picture when they draw it. this is what I was trying to show you, where the center of curvature would move from when the object was along this part of the path to when it was along this part of the path. And so the other thing that we use is this term radius of curvature, which is, we use the Greek letter rho. You might like to think of it more as an R, but the radius of curvature is kind of a little bit more general and kind of implies the fact that it can change as we go in different parts of the path. Obviously, the radius of curvature over here is different than it is over here. Okay, so when we're talking about the motion of this object, for one, we still have the velocity as tangent to the path. And so the velocity vector can always be written as the speed times the tangential unit vector. We already have established that the velocity is always tangent to the path, and so that makes perfect sense. In terms here, this is the magnitude of that vector, and that's just, what's its speed. Now, this is where things get tricky, and we've done this before, but I'm going to show you again because we're going to use this quite a few times. So if our velocity vector is written as the speed times the tangential unit vector, when we find the acceleration, we're finding the derivative of that velocity vector with respect to time, which actually means that we have to do two things. We have to use the product rule. So one component of the acceleration is tangent to the path and is due to the changing speed. But then there's another component of the acceleration, which is found when we take the derivative of the unit vector. And essentially what we're looking at is this changes because its direction changes. The length of the unit vector isn't going to change, just its direction. So we have to figure out how to write that. Like, how do we quantify the change in the unit vector? So the first thing we're going to look at is we're going to look at the magnitude first. Because in a sense, the change in that unit vector is going to have a magnitude, and we're also going to have a direction. So in this picture right here, they've done a really nice thing, is they've taken this picture and they've put the two tangential unit vectors tail to tail so that we can look at their change. And so again, we're looking at the magnitude of that change. Now there's something that we use with a circle. And so when there's a angle that subtends an arc length and you have a radius, we find that the arc length is equal to the radius times that angle. So we're going to use that here to figure out how to write this du, because it's like our arc length. We're going to write it as the angle, which is d theta, and then the radius, which is just the tangential unit vector. And then we'll use that magnitude, which is just equal to 1. So really the magnitude of du tangent is just d theta. And then if we want to find the magnitude of du dt, we just take that d theta and divide it by t. And so we can express that as this, or we can express it as the angular velocity. Okay, so what we have found so far is our acceleration, which is it's dv dt times u tangential, plus v times du tangential dt. No, right, I shouldn't be making absolute values of that. That's just times s. And we found that du tangential dt can be expressed as theta dot or omega. But what's the direction? And if we look at this, we notice that these two are parallel. So the direction is in the normal. So you can see that the direction that this points tends to be the same as the unit normal vector. So if we put this all together, the acceleration that we can express when we use normal and tangential unit vectors can be written as a component that is tangent to the path is caused by a change in the speed of the particle, and then another component that is normal to the path is equal to velocity times omega. Now that might not look as familiar, but if we do a little bit more with that, remember omega, angular velocity, can be written as velocity over rho. And this is equal to dv dt ut. And so this is the tangential component of the acceleration, and this is the normal or the radial component. And so that makes sense if we think about it, because that's what we said at the beginning. When you have acceleration of an object moving in a curve, it can be caused by two different things. It can be caused by a change in the speed of the object, or it can be caused by a change of direction. And that's what these two terms are. And so it doesn't look too good, but here we'll say that the tangential component of the acceleration again is caused by a change in the speed, and the normal component is caused by a change in the direction, which is, if you recognize this is centripetal acceleration. And then we can find the magnitude of the acceleration can be found by taking, again, using the Pythagorean theorem, taking the square of each component and taking the square root of those. Okay, so here we're going to be looking at a particular situation. Okay, again, I'm going to rewrite it. The radius of curvature, this boat's going in a circular path with the radius of curvature of 40 meters, and its velocity is equal to 0.0625 t squared meters per second. And we want to find the velocity and the acceleration at t equals 10 seconds. And that's going to be another problem that I'm going to leave for you to give a try. And when we meet as a group to go over problems, this is one of the ones that we can go over. All right, I know that was a long one. If you can't listen to it all at once, break it into pieces. And we'll be getting together on Wednesday to talk more about the class. Hope all is well.